Great. Thank you very much. So indeed, thanks to all of the organizers for putting on such a wonderful conference and also a wonderful program in which this is situated, and for the opportunity to talk, and thank you for all of you for being here. So indeed, the title of my talk is Higher Symmetry Phenomenology, or if you wanted to be very specific about what I'm going to go into, Emergent Higher Symmetry Structure and Particle Phenomenology. And I realize most of you are not particle phenomenologists and with good reason may not care at all about particle phenomenology. But one of the beautiful things about generalized symmetries is it provides us with a language that makes our problems mutually intelligible across fields. And so one of my goals will be, even if this is something that you haven't ever thought about or cared about, to help you become interested in it. But also then there's, of course, also particle theorists and phenomenologists in the audience. And then the other goal of my talk is to help maybe communicate to you how methods in generalized symmetries, I think, should be increasingly relevant. And I'm going to say a lot of the statements that I'm going to make in this talk, probably all of them, are going to be blindingly obvious to someone in the audience. And my hope is only that the different blindingly obvious statements are obvious to different sets of people. Finally, I should say all of the really interesting things I'll say that are new are based in part on work with my graduate student, Dan Sahayek. And Dan is, again, a real testament to the awesomeness of generalized symmetries and that he's able to live very productively at the interface between condensed matter theory and high energy theory. Okay. So just a sort of motivational comment about my background and my title slide. If you're a particle theorist, I think it's fair to say that we in some sense spent a long time living under a lamppost in terms of thinking about physics that might lie as a microscopic description beneath the standard model. And that lamppost was dramatically upset by the last decade of experiments, whether they be colliders or other experiments. And now we're in a period of recognizing that, outside that lamppost, there's a sort of vast universe of interesting possibilities for particle physics, and we're going about exploring it. And there's two reasons why generalized symmetries, I think, play an important role in this evolution. One is that, of course, it's a powerful set of theoretical tools, and bringing those tools to bear on the problems of particle physics is bound to be interesting. But there's a second one, which is maybe also a message for particle physicists. 40 years ago, there was a really beautiful intersection between topology and particle physics, right? There was a huge development of the understanding of the topological structure of field theories in 2+1 dimensions and their observational consequences. And then we sort of lost attention, where our focus drifted away and really focused on the search for new particles at colliders. But as it becomes harder and harder to hope for the discovery of new particles at colliders, there's a reminder that topology is still there, and in fact, we have far from explored all of its interesting experimental consequences. And maybe one thing we should do as a community is turn our attention back towards those things. So I think we're at the start of a beautiful revival of relevance of topology to particle physics, and I'll try to give you some motivation for a specific version of that today. Okay, I should say, a talk titled Higher Symmetry Phenomenology would have to do justice to a lot of amazing work that's been happening over the last few years, especially driven by many people who are here in this room. What I'll tell you about today touches on parts of this, but I just wanted to put many of these things up here for the work that I'm not going to have a chance to touch upon. Okay. So to say some very basic things, to try to build some bridges between different parts of the audience. What do I mean by higher symmetry structure? Well, as we've observed, of course, anytime we have ordinary and higher form symmetries, anomalies, connect these symmetries of differing degrees in interesting ways. Of course, there's a superabundance of ways that can happen. But in particle physics, there's really two cases that I think we often care most about. The first one is when we have 't Hooft anomalies that either just involve the zero-form global symmetries of our theory, or maybe the zero-form symmetries in one factor of a gauged symmetry. And as we've known now for some time, that gives rise to a higher group symmetry structure. And what's interesting about that, of course, is that now mixes, in some sense, the zero-form symmetry with a one-form symmetry in the case of a two-group. So to suggest why that's the case in a language that's familiar to particle physicists, for example, there's a operator-valued contact term that appears in the OPE of the divergence of your global symmetry current with another operator, and this is a sign that your zero-form symmetry now is tied up with the one-form symmetry of your theory. The second case that often occurs is, of course, when instead of having 't Hooft anomalies, we have genuine ABJ anomalies, and then we know that the residual symmetry of the theory is non-invertible, as people here in the audience have taught us a few years ago. And here again, now that tells us there's some co-involvement of your zero-form symmetry with a higher form symmetry, and that can be seen, for example, by looking at what happens when you bring together two of the non-invertible symmetry defect operators. They typically now involve insertions of operators relevant to the higher form symmetry. Okay, so here, the details of higher group and non-invertible symmetries, I don't particularly need to get into. The thing that matters is that in these cases, we have this higher symmetry structure where the zero form symmetry is no longer a good symmetry on its own, but is tied up with a higher form symmetry. And that has interesting dynamical consequences that are relevant to particle physics. So the sense in which they're relevant is that, of course, it's also the case in particle physics that many of the symmetries we care about, especially the higher form symmetries, are emergent in the infrared. They're explicitly broken by various degrees of freedom in the ultraviolet. And so each one of them, of course, can emerge at a different scale. But when we have these higher symmetry structures, there's in some sense the lower degree symmetry, which is the bad symmetry, and it's fixed up by the presence of the higher degree symmetry, which is the good symmetry. And so that means if these symmetries all emerge as a function of scale, the good symmetry has to emerge before the bad symmetry can be a sensible symmetry. Now, these are fuzzy inequalities, so at the very least, we maybe mean that the good symmetry can't emerge dramatically below the scale of the bad symmetry. And this observation of this interesting consequence of emergence, these emergence inequalities, was pointed out, of course, in the very earliest works exploring higher group and non-invertible symmetries. But I just want to emphasize, the relevance for particle physicists, right, is any effective field theories that we care about as particle physicists, they're rife with these emergent higher form symmetries and higher symmetry structure. And so because they're subject to these emergence inequalities, that means any UV completions of our favorite effective field theories have to obey this. And the way in which they'd obey it, of course, that's a very powerful input. And there are a lot of observational consequences that we can try to look for experimentally. Of course, to make use of this, you have to have a well-defined notion of, what is the scale at which a symmetry emerges, which becomes, a little bit more complicated as the symmetries become higher and higher degree symmetries. There's been some very nice work exploring this. One of the messages of my talk is, we don't currently have very precise statements about the emergence scales of higher form symmetries, and making those statements more precise should be very interesting. And so we can continue to build on what we've understood so far. Okay, so to articulate why this matters and why it might be interesting for particle physics, I want to start with a canonical example, which was really beautifully explored by Clay and Daniel a handful of years ago, which is an axion coupled to Yang-Mills in 3+1 dimensions. And this is for particle physicists. Again, we've had this What is Particle Theory program going on at KITP. It's ending this week after 14 weeks. And we've had over 100 talks, and I think about 20 of them involve axions. So as a statement about what the field cares about, it absolutely cares about axions. But here we just have the idea, we have some periodic scalar, which is coupled to let's say, an SUN gauge group through an anomaly term. And the free theory, of course, has three global symmetries of interest. It has the non-linearly realized zero form symmetry of the axion, its shift symmetry, which is broken by its coupling to SUN. The SUN itself, of course, has a ZN center symmetry, and then the periodic scalar also has a two-form winding symmetry. And we recognize now that the two-form winding symmetry and the one-form center symmetry together participate in a three-group structure. So the two-form symmetry is the good symmetry, the center symmetry is the bad symmetry, and so this emergence inequality argument tells you that if these symmetries emerge as a function of scale, the winding symmetry should come before the emergence of the center symmetry. And so, this is something that Daniel and Clay explored in their original paper. They said, well, okay, great. If this has to be true of any UV completion, let us write down the simplest 3+1 dimensional UV completion of the theory we can imagine and see how this emergence inequality plays out. So the simplest UV completion you could imagine for that effective field theory is to write down what we would call a KSVZ type axion. That is to say, there's in the UV, there's some scalar. It's charged under an ordinary zero-form global symmetry. There are some fermions that are also charged under the symmetry. So, of course, the scalar gets a VEV. It breaks this global symmetry. The fermions induce an anomaly, and that's what couples, at the end of the day, the axion, which is just the angular mode of the scalar, to the SUN gauge group at low energies. Okay. So there's one important scale of interest, which is the scale of the global Paget-Quinn symmetry breaking. And then that feeds into, there's a mass, of course, of the radial mode, the massless axion, and then the mass of the fermions, which they pick up from their Yukawa coupling. So now you can ask, okay, how do these, what are the emergence scales associated with these symmetries? So it's pretty clear that the one-form symmetry emerges below the scale of these fermions. They have non-trivial anality, and so they break the center symmetry of SUN. So that's clearly the fermion mass. It's a little more ambiguous what you mean about the emergent scale of the two-form winding symmetry. There's three relevant scales. There's the scale of the radial mode itself, which starts to tell you that you don't just have an axion at low energies. There's the scale associated in some sense with the tension of the global strings that are generated as topological defects from the symmetry breaking. And then there's maybe an intermediate scale, which is associated with the potential energy required to go from the bottom of this potential to the top. And the most conservative emergence criteria you might apply in this situation says, well, certainly if I'm at energies of order of the string tension, these strings are dynamical objects, and that would break the two-form winding symmetry. And so naively applying that criteria tells you, in some sense, that the Yukawa coupling has to be small. But something surprising happens. Something goes wrong well before you hit that scale. And in particular, indeed, if you tried to pull the scale of the fermions well above this intermediate scale, you observe that at that point, the quantum corrections to the potential of the scalar coming from loops of the fermions actually destabilize the vacuum. So there's some radiative correction, which goes like 4 powers of the Yukawa coupling, and it enters with the sign that wants to destabilize the vacuum here. And so if you attempt to lift the fermions well above this intermediate scale, which is sort of before you hit the scale, it really depends on the value of the quartic itself, the theory is destabilized. Okay. So this is an interesting phenomena. In some sense, the physics that satisfies the emergence criteria comes in parametrically before it actually had to. And partially that's because in this completion, all of the objects, including the vortex string, are extended degrees of freedom. Of course, what do particle physicists like to do? For every EFT you write down, we can write down a million UV completions. And so it is interesting to ask, if I went away from the simplest UV completion to some more complicated UV completion, would I still see the sort of same phenomena happening? So another example of how you might get this Axion-Yang-Mills EFT at low energies is actually to start in 4+1 dimensions. You could imagine there having a U1 gauge theory and an SUN gauge theory living the bulk. You compactify the 5th dimension, maybe with some boundary conditions. And at low energies, the 4-dimensional effective theory looks like the Axion-Yang-Mills theory I've described to you, where the axion is now coming from the 5th component of the U1 gauge boson. So there's a very nice map. Again, the beauty of generalized symmetries is it allows us to understand very nicely the relation between the symmetry structures of the full theory and the EFT. So the electric one-form symmetry of the U1 in 5 dimensions becomes the zero-form symmetry of the axion in 4 dimensions. The center symmetry of SUN just goes across the compactification. And the magnetic two-form symmetry of the U1 in 5D becomes the two-form winding symmetry associated with the axion in 4 dimensions. So now you can apply the same sort of question. We have these emergence criteria, and how are they satisfied in this UV completion? Well, there's something very silly that could happen, which is, as we know, 5-dimensional gauge theories are not UV complete, and so it simply could be that all of the symmetries emerge at whatever the cutoff of the 5D theory is. But you can give the theory a little bit more structure to see something interesting, and you can imagine instead that before you hit the cutoff of the 5D gauge theory, this U1 that the axion lives in actually comes from an SU2 that is simply broken down by an adjoint Higgs. And if there are fermions that are charged under both of these groups, then once we Higgs down, that will generate the Chern-Simons term that's necessary for the axion coupling. Okay, so now we could ask the same questions about how the emergence criteria are satisfied. Again, the center symmetry, the bad symmetry, emerges at the scale of these bulk fermions. There are, again, sort of 3 interesting scales for, in this case, the monopole string, which is the object that breaks the magnetic two-form symmetry. There's the size of the radius of the monopole string, which depends on the gauge coupling. There's, in some appropriate units, the VEV of the scalar itself, and then there's the tension of the 5D monopole string. And something, again, very interesting happens, which is very reminiscent of the previous example I gave you, which is something goes wrong, in fact, if you try to pass the mass of the fermions above even the lowest of these scales. Once you try to pass the fermion above even the lowest of these scales, again, the gauge contributions and the Yukawa contributions to this scalar potential are competing. And so if I try to pull the mass of the scalars well above this lowest possible scale, I destabilize my vacuum. So again, it's a very, these emergence criteria in these perturbative examples are sort of unreasonably effective. Not only are they satisfied, but they are satisfied in ways that sort of don't even seem to be directly related to the underlying symmetries. So this is just an argument that, there's any time in an EFT for particle physics we have these higher symmetry structures, the emergence criteria can tell us very interesting things that we may not have been awake to. Of course, I can imagine what some of you are thinking right now, apart from when is lunch, and that's these arguments. These arguments that I've given you. I'm always working in a field theoretic UV completion, in which, for example, I can probe the string-like objects that have finite size. But it's also possible to have UV completed this Axion-Yang-Mills EFT with a UV completion that is, for example, string theoretic in nature, in which the string objects are fundamental. They don't necessarily have a size. And so there must be some general effects that we haven't encountered in my description so far that ensure that this emergence inequality is satisfied. And indeed, we've known about this phenomena for 40 years now. It's the physical phenomena of anomaly inflow, which just tells us that there are charged zero modes that will be living on the string, and those charged zero modes suffice to violate the center symmetry in this example. So the slogan really is, apart from the perturbative phenomena I've described to you, on top of that, even in non-perturbative UV completions of this EFT, the fact that there's an object that breaks the winding symmetry, so a dynamical string, plus some sort of anomaly term, in this case involving the axion coupling to SUN, tells us that anomaly inflow will automatically enter at the right scale to violate the center symmetry. And it saturates the inequality because the zero modes in some sense are associated with the fluctuations of the string. Okay. Now, in the 4D UV completion that Daniel and Clay studied, it's very easy to see what the physics is, right? These zero modes are not mysterious objects. Once you go to the core of the string, you've also restored the global symmetry, and these bulk fermions become massless at the string core with some exponentially suppressed profile. And so there's no mystery here. These ingredients were already present in the theory, but they really tell you why it is that once you introduce a string, there are zero modes, massless fermions that are living on the string. But, again, if you go to non-perturbative UV completions of the same EFT, there are degrees of freedom that must appear that are not apparent from low energies. And these are, for example, various charged worldsheet excitations of fundamental strings in the case of F and D strings. So, if you wanted to give a slogan, of course, that explains all of these things in a very simple way, it would be this nice, very general statement that anomalous symmetries end at the boundary, in this case, the boundary being the boundary provided by the string. I want to give you a closely related example, which is something that, particle physicists care a lot about Axion-Yang-Mills, but maybe they care even more about Axion-Maxwell theory. Oh yeah, go ahead. Sure.
So before you talk about this zero mode, so some anomaly inflow to the strings, and then that will explain the equalities, but then that assumes that the energy gap of the excitations on the strings are very tiny, right?
So indeed, in the perturbative example, absolutely, these are just massless fermions that live on the string.
That's
in
right.
the non-perturbative case, in the case where, for example, they're fundamental strings, it's not at all obvious.
That's right.
Yeah, so indeed, so for me, this is a very beautiful and satisfying explanation. Here, it really, one then needs to establish that in fact it's always the case that the excitations are relatively accessible.
Yeah.
And I think, this is, in some sense, this is what, Ben and Matt and Tom argue. It would be interesting to find examples where this is not obviously true, just because, then there would even be more substance to the emergence inequality, right? It would tell us, So probing this, I agree, is an excellent statement. In perturbative completions, it's sort of obvious.
Yeah, that's right. I agree. Yeah. Thanks.
Yeah. Okay. So an even more interesting example in some sense is to replace the non-abelian gauge theory with an abelian one. And again, this was beautifully articulated by folks who are all here. And so now we're thinking about a similar story where now the axion is just coupled to a U1 gauge theory. Now here, of course, there's more global symmetries of the free theory that are interesting to us. There's still the shift symmetry of the axion. There's now the one-form electric and magnetic symmetries associated with the U1. And there's, again, the two-form winding symmetry. And here, of course, this AFF dual term does now more interesting things in this example. In particular, it renders two of these symmetries non-invertible. So the zero-form symmetry becomes non-invertible due to this interaction and is now linked to the one-form magnetic symmetry. And the one-form electric symmetry also becomes non-invertible in a way that's connected both to the magnetic symmetry and the two-form winding symmetry. Okay. So we can apply the same arguments, of course, for emergence. The fact that now there's a non-invertible symmetry, this Peschek-Winn symmetry is non-invertible, tells us the shift symmetry which is associated with this, should emerge below the scale at which the magnetic symmetry emerges. And then the non-invertible electric one-form symmetry tells us that it should emerge below the scale of both the magnetic symmetry and the winding symmetry. And in some sense, this set of inequalities is stronger. So this doesn't have any higher group symmetries. We could induce some if we change the coefficient of this term. But parametrically, these are a stronger set of constraints than the higher group constraints. So as we just said, of course, the emergence of the electric symmetry should be satisfied by inflow, of course. In the case of the winding symmetry, it's inflow on strings. In the case of magnetic symmetry, it's the analogous phenomenon on monopoles. So the monopoles should support some dionic excitations. And again, per Hotat's question, this does, of course, now require something about the separation of the dionic excitations from the monopole itself to ensure that this inequality is satisfied. So there are interesting things to check here, that in fact dionic excitations of monopoles can't be sort of arbitrarily separated from the monopole mass scale itself. But at least we can identify the phenomena that's at play. But this other inequality, the one coming from the zero-form symmetry becoming non-invertible, is less obvious. There's really no ingredients we've encountered so far that would satisfy the emergence inequality. Except for a calculation that was done a few years ago, which I think is an incomplete calculation, but points us in a direction that is very interesting and relatively new, certainly for particle physicists. Okay, it's not that new. We know, of course, in theories that have instantons, that low energies, there's some correspondence between the effects of instantons and the effects of monopoles, but making that precise is something that has yet to be completely done. And so what the folks at Harvard did was carry out a calculation, a world line calculation, where if they had a monopole and a tower of dionic excitations for, under a U1 theory, the mass spectrum, of course, of these things through the Witten effect depends on the theta angle. And so now if we coupled an axion to this theory, the axion would also appear here. And so the mass spectrum would depend on the background value of the axion field. And now we could imagine integrating out all the dions, and that should induce an effective potential for the axion. So that was a calculation that was done in this paper, again, in a restricted context. But indeed, it bears out this expectation that, so the axion, of course, now is the thing that has the shift symmetry. If it gains a potential from loops of monopoles, the scale at which that symmetry is broken really is the scale at which the monopoles appear, or rather, the monopoles and their dionic excitations. Okay. So this is a really interesting effect, and again, it's relatively new for particle physicists, but it demonstrates the satisfaction of the emergence criteria. There are directions that this needs to be pushed. You can, for example, repeat this calculation in a theory where you give structure of the monopoles, for example, making them topological monopoles. And there's really is a suggestion that there's a direct connection, of course, to what you would have seen as instant contributions from the UV theory. But making this map complete is something that has yet to be done, so there's a lot more opportunity here. This is not really talk about particle phenomenology, but for those of you who don't think about particle phenomenology, I want to emphasize why all of this matters. So we've known about phenomena like anomaly inflow for 40 years, but there is a really increasing recognition over the last few years that this phenomena has experimental consequences in our universe, even at late times, that would potentially be observable. So just to give you one example of it, the axion that we believe may be there to explain the smallness of CP violation in the strong interactions, it gives rise to axion strings. Those strings have anomaly inflow of both electromagnetically charged particles and QCD charged particles. And then that means if you have one of these strings passing through the early universe or even the late universe, magnetic fields in the universe will actually charge up these strings. That accumulated charge will generate large electric and magnetic fields. Those fields actually will then lead to Schwinger pair production of standard model particles around the string, and then some of those particles will accumulate around the string in bound states. And the interactions of these bound states, even at current times, gives us interesting observational consequences. So anomaly inflow, far from being some abstraction in the space of these theories, is something that actually is giving us new experimental handles if these objects exist in our universe. Okay. So there are many examples of this in the last few years, but I want to say there's profound experimental consequences of better appreciating this picture. Okay, so I've given you a couple of examples where the infrared theory, the anomaly is saturated or is appearing in connection with some bosons. I also want to talk about examples where the infrared theory, the anomalies are associated with fermions in the EFT. And what better way to do that to demonstrate its relevance than to talk about the standard model of particle physics. So, of course, in the standard model, we have the gauge group, SU3 cross SU2 cross U1. Also, in the space of generalized symmetries is the question of what the global structure of this group is. That's a very interesting question, but not my interest today. We have 3 generations of 5 types of fermion field charged into that. And then, of course, we have the Higgs boson. And if we turn off the Yukawa interactions in the standard model, then there's a large set of global symmetries associated with the rotations of the fermions. Okay. And so, if we want to understand the generalized symmetry structure of the standard model, it is productive to turn off the Yukawa interactions, which should just be some perturbative adjustment of the story, and really understand the consequences with respect to these global symmetries. So of course, because the standard model has an abelian gauge group, that means it has a magnetic one-form symmetry. And the fact that we have that plus abundant flavor symmetries means that there should be an extensive higher symmetry structure associated with both two groups and non-invertible symmetries. And we should figure out all of the interesting consequences of that. So of course, the first and very useful step in that direction was done by Clay and Seth a few years ago, which was indeed to focus on the flavor symmetries of the standard model and the two-group structure that they form with the one-form symmetry, magnetic one-form symmetry of hypercharge. And so the observation they made in this paper was that if you consider any one of these flavor symmetries of standard model fermions, any one of them on its own has a 't Hooft anomaly with hypercharge. But by inspection, so this is the anomaly coefficients in my choice of normalization, but of course you can see, you could take combinations of these flavor symmetries, diagonal combinations of them, where the anomaly would cancel. So any individual one has a 't Hooft anomaly, but combinations are anomaly free. And in this case, the emergence inequality means that, if the magnetic one-form symmetry emerges in the UV, because, for example, we pass through the scale of some monopoles, that should always happen above the scale at which these flavor symmetries are good symmetries. And this has a very powerful consequence if we imagine unifying the standard model gauge group into a grand unified theory, because we know that, in fact, the grand unified theories produce monopoles under which hypercharge is charged. So the observation that Clay and Seth made was that this actually can give you a simple way of seeing what combinations of fermions you can unify into multiplets of a grand unified theory, because it is only the combinations of fermions that don't have a 't Hooft anomaly that can be consistently unified compatible with the emergence inequality. Okay, so that's a very nice result. And here, what they're leveraging is, again, in some sense, a perturbative consequence in the ultraviolet, right? What would happen if you tried to put fermions with an anomaly into unified multiplets is the gauge bosons, the exchange of gauge bosons at tree level even, would violate those flavor symmetries. All right. But much in the Axion-Yang-Mills example, you expect that, of course, in a perturbative UV completion, fine, there's some perturbative physics that maybe enters before it has to. But there must necessarily also be very general effects that ensure that the constraint is always satisfied. And again, this is due to something that we've known for even longer than we've known about anomaly inflow, which is the violation of global symmetries in monopole fermion scattering, the Kalin-Rubakov effect. And of course, there's two parts to the Kalin-Rubakov effect, right? There's the still controversial part, which is that in certain situations, it's not obvious that the outgoing states are in the Hilbert space. There's the much less controversial bit, which is that they're simply global symmetries that are broken and scattering off of monopoles. And what's been beautifully stated in a couple of papers a couple of years ago is that, in fact, there's just a very precise connection between zero-form symmetries that participate in a two-group in 4 dimensions with a magnetic one-form symmetry and the global symmetries that are broken and scattering off of monopoles. So being part of a two-group structure means you are one of the global symmetries that's violated by scattering off of monopoles. One way to say it is that when you have the two-group structure, if you go down to the two-dimensional theory that you can use to study the consequences of scattering, there's a 't Hooft anomaly that forbids symmetric boundary conditions and ensures the symmetry is broken. So this tells us, while there are perturbative phenomena, exchange of unified gauge bosons that violate these global symmetries, again, there's an effect that must enter to always guarantee that the physics is satisfied, and this is monopole catalysis. So why am I telling you this? Well, the two-group symmetry structure of the standard model is very interesting, but it's only part of the story. So indeed, in addition to the 't Hooft anomalies of various standard model flavor symmetries, there also is an abundance of ABJ anomalies. So here I'm just considering the flavor symmetry of any one generation of these standard model fermions. Of course, many of them have anomalies also with the weak interactions, which simply breaks them down to a discrete subgroup. But there are many of them that just have anomalies with hypercharge. Of course, there's also anomalies with SU3. And so it's very interesting to think about what the emergence inequalities associated with the non-invertible parts of the global symmetry structure can tell us. So we could spend all day talking about some interesting consequences, but I just want to focus your attention on one of them, which is you can make a combination of these flavor symmetries, which is baryon plus lepton number. So that's the Q number minus the U number minus the D number divided by 3, plus the L number minus the E number. That's the symmetry. Now, of course, it has an SU2 anomaly, but the emergence inequalities should still tell us something, even if we imagine that SU2 instantons weren't breaking the symmetry, because the symmetry still also participates in a higher symmetry structure with hypercharge. Okay. So I just want to give you a specific example where this points us to something that we haven't paid attention to, and we could have paid attention to at any point in the last 40 years, but now we're reminded that it matters and maybe it has experimental consequences. So the emergence criteria, so again, U1 baryon plus lepton number, it tells us there's some higher symmetry structure with hypercharge, so if they're monopoles of hypercharge, there are effects that violate U1 baryon plus lepton number. This is not at all interesting if we unify the standard model into a simple group gut like SU5 or SO10. We already know that those groups break baryon plus lepton number, so there's really nothing we've gained. But I want you to consider another very interesting unified gauge completion of the standard model, which is what's known as the Patti-Salam unification. This puts leptons and quarks into the same multiplet, and so we say that lepton number becomes the fourth color. And the reason this example is interesting is that even though this Patti-Salam unified group puts baryons and leptons in the same multiplet, it preserves baryon plus lepton number as a symmetry. And that's because it remains an accidental symmetry of the gauge interaction. So the exchange of Patti-Salam gauge bosons doesn't violate baryon plus lepton number. Okay. But we know from the emergence inequalities, right, that if Patti-Salam theory gives us monopoles, baryon plus lepton number should be violated in monopole scattering. And at the very least, it should be violated down to some subgroup of baryon plus lepton number, which depends on the number of standard model generations. Okay. And in fact, this was computed by Sen in 1984, who was interested in precisely studying the consequences of the anomaly for scattering off of Patti-Salam monopoles. And so what's very interesting about it is, at least because the piece of the baryon plus lepton number violation that is suggested by the ABJ anomaly with hypercharge preserves the Z6 subgroup of baryon plus lepton number, that means that these processes should only violate baryon number by 3 units. And indeed, that's what Sen found. It was somewhat mysterious at the time they did the calculation. The exact reason that this is true, you simply find that condensates that violate it by fewer numbers vanish. But now we have a very simple way of understanding why that's the case. And the reason why, so this is something that we are reminded of, and there's in fact a much richer structure now of monopole-mediated processes. And the reason why this is experimentally interesting is you can ask, well, what is our current state of experimental knowledge about monopoles from grand unified theories? I don't expect you to be able to read this in the back of the room, but as a function of, say, the velocity distribution of the monopoles that we might be seeing, you can set a bound on the upper limit of the flux of the monopoles. There are lots of bounds that come from various things, like not disrupting magnetic fields in the universe, or simply looking for monopoles directly on Earth. But dramatically stronger bounds, by 10 orders of magnitude, come from considering monopoles, for example, in SU5 or SO10, that mediate baryon number violation by 1 unit. And where these bounds come from is that if such monopoles existed, one of them would, in all likelihood, end up being captured by the sun, and it would sit there in the sun, catalyzing proton decay and producing neutrinos that can be picked up in terrestrial experiments. Okay. So if you believe in grand unification and monopoles from grand unification, you might be very pessimistic about the prospects of ever seeing anything given these bounds. But these bounds, crucially, are assuming that the processes that are effective here violate baryon number by 1 unit. And in this much more interesting case, where baryon number violation is by 3 units, the story is dramatically different. So we actually don't know where the state of experimental sensitivity lives, but there's 10 orders of magnitude between other bounds that don't really care about this, and the bounds that we think are relevant for gut monopoles, where we could have experimental signatures of this phenomena, and we don't yet know it. Okay, so this is just another example where generalized symmetries, the higher symmetry structure, and thinking about the emergence criteria points us to physically observable effects that we should go out and look for. Okay. I should say this isn't the whole story, because of course, once you think about the anomaly-free subgroup of B plus L in the whole Patti-Salam theory, it breaks all the way down to Z2. That means there's Patti-Salam instantons that violate the symmetry further, but that may also mean that there's a more interesting structure of the full set of monopole catalyzed processes. Okay. So that brings me to the end. So as I've tried to argue at the beginning, 40 years ago, symmetry and topology played an enormous role in particle physics, and that sort of faded from, I think, the central questions people were asking over intervening decades. But as we find it harder and harder to look for evidence of new particles, looking for evidence of new phenomena associated with topology of our fundamental theory is something that we should absolutely be doing, because there's immense opportunity. And, you know, the beautiful thing about generalized symmetries is now it gives us a very systematic language of categorizing and classifying the phenomena that we could hope to look for. The thing I've tried to focus on today is when we have higher symmetry structures, these emergence inequalities are a powerful guide because we have many EFTs that have these structures, and necessarily that means there's phenomena that we can look for in many different UV completions. As we've seen, satisfying these inequalities, it systematically organizes what you might call familiar phenomena, so anomaly, inflow, and monopole catalysis. However, you know, even invoking those phenomena doesn't tell us the entire story. Again, as Hotat's question alluded, in cases where we don't have a perturbative UV completion, it's actually far from obvious that the phenomena itself guarantees the inequalities are satisfied, so we have a lot to learn there. It also, even that phenomena reveals new effects. So one example being a calculation of virtual monopole corrections to Axion potentials, which opens many doors for interesting possibilities downstream. But it's also the case where even when the UV completions of our EFTs are perturbative, these emergence inequalities are sort of unreasonably effective, right? They tell us actually that the inequalities are satisfied before they even had to be, sometimes by parts of the theory that weren't obviously connected to anomaly inflow or monopole catalysis. And so there's a lot more we can stand to learn there. There is absolutely room to sharpen the meaning of the emergence scale, so as to say what these energies are. A lot has been done so far, but I think there's a lot more we could do, and the more we do, the more we're able to put this into productive effect. And again, although we've been reminded by these phenomena of anomaly inflow and monopole catalysis, there may well be other effects that are connected to these emergence inequalities that the generalized symmetry experts in the audience know about that particle physicists don't, and so that's also a profound opportunity. And then on the particle physics side, you know, I've tried to give you some examples of things we can do now that we didn't do a few years ago. There are many, many more, and well, there's a whole universe out there that we can now turn to exploring. So thanks very much.
Thank you for the very nice talk. So I wanted to ask more about this relation between proton decay and monopoles. So in the vanilla standard model, the G3 subgroup of the UN baryon number is safe from ABJ anomaly, and then it will protect the proton decay, right? But this relation to monopole, maybe it suggests there might be some higher group structure between this G3 symmetry and then UN magnetic one-form symmetry for the electromagnetism. If this is, I'm not sure if it's there or not, but if there is such a higher group, then it might be very interesting because it will mean that in any grand unification, so there will be dynamical monopoles, and then that will always mean that proton must decay. Have you thought about such a possibility?
So yeah, I think the current state of knowledge is, of course, the awareness of the discrete subgroup that's preserved by the standard model, by its anomalies with the electroweak group. Further higher structure associated with that, I don't think has been fully explored. And indeed, while it's the case, you know, for example, also in Padi Salam, where the example that was computed by Sen suggests that that the violation is in the monopole scattering is stuck at delta B is equal to 3. It may well be that there are other monopole configurations, for example, that are maybe not the lightest one that he didn't study that violate it by more. So indeed, this is one of the things that I'm hoping can be productively explored, is if we can better understand and classify the higher structure of the residual baryon number of the standard model, we should be able to map out the spectrum of baryon number violating processes more completely.
Thank you.
No, it's just a trivial comment to this, that in standard model, you do have baryon number violation, right? And it could be reflection of a little bit of this kind of monopole possibilities.
Absolutely.
You see, kind of indirect.
Yes, of course. So indeed, right. So as already alluded to, the standard model itself breaks B plus L down to a discrete subgroup. There are therefore processes, as we know, as ailerons, we believe operative in the early universe. Absolutely. It's just interesting that even at zero temperature, right, in the presence of monopoles, we also have baryon violating number effects. And so simply having something that persists in our universe is an interesting probe. And indeed, the full connection between all of the monopole mediated processes and all of the instanton mediated processes, to my knowledge, has not been fully articulated. And so this is just a huge opportunity to do that. Right? Okay, time for lunch.
Yeah, if there are no more questions, we can thank the speaker again.
Thank you.